It's 3 p.m., so we can start now. So welcome to the Introduction to Material Science and Engineering course, where we are in the week 8. Let's quickly have a look on the list of the content that has been covered till now. The content that has been covered is like last week we discussed about the eutectoid, hypereutectoid, and hypereutectoid steel. In this particular week, we discussed about the microstructures of the how the eutectoid steel is evolving. Also the hypereutectoid, how the microstructure is evolving from the liquid to the going to the solid phase. So these three first topics are mostly we have covered in the week 7 also while solving the doubt solving in the doubt solving session. Now after this, the phase diagram has been completed. The introduction of the phase diagram and the microstructure evolution has been completed here. Later on, now the entire discussion of this particular week 8 is on the diffusion. So we discuss what is the diffusion. There are the two laws in the diffusion, which is a fixed first law and a fixed second law, where we saw that how the flux is changing. Flux is negative of dc over dx. This is the fixed first law we have. We know that. And the second law, we know that it's like it's relating the concentration gradient, how the concentration is changing with the time. It's relating it with the rate of the concentration with the spatial variation. So we can see here on the left hand side, the change in the concentration is with respect to the time. While on the right hand side, we can see that the concentration change we are seeing in from the perspective of the space, from the distance. So the second derivative of the concentration with respect to the space is equal to the first derivative of the concentration with respect to the time. So this is the fixed second law. After that, we discuss, like, since we know that this is nothing but a differential equation. Okay, every differential equation will have the solution associated with them. Okay, so when we solve we got the function to be the error function, which we will again discuss. Later on, we discuss the derivation of the fixed first law from the atomistic mechanism. Okay, we derive this particular equation. Then we move to the substitutional diffusion. Then we from the substitutional diffusion, I mean that how this diffusion kinetics, in what way the substitutional is differing from the interstitial. And in the class we have saw that in the interstitial we only need the activation energy for the migration, because lot of the interstitial sites are empty. But for the substitutional, we know that the diffusion mechanism is the vacancy. So not only we need the migration, like the activation to migrate the vacancy, also we need the energy for the formation of the vacancy. Okay. So in this way, the substitutional diffusion will vary from the interstitial, and the whole the entire the most important thing that we have to remember that in the substitution we also have to form the vacancies, while in the interstitial we already have a sufficient amount of interstitial sites which a particular interstitial atom can take. So this formation is the additional part over here in the substitution one. Then we discuss about the diffusion path. We saw that the lattice is there, we have the grain boundaries, then we have the surface. In all of them, what is the variation in them? It's the broken bonds. Okay, and the lattice is the most stable. So if I want to move anything in the lattice diffusion activation energy will be very high. So to facilitate the diffusion in the lattice through the lattice, it will require more temperature because the activation energy is high. While for the grain boundary, the activation energy will be lower than the what we can say in the lattice. Okay, and then for the surface will be even lower. So whenever we see for the you take a powder, you compact it and put it for the heating. So first thing that will happen with the surface, because the first diffusion that will happen will always be the surface diffusion. It cannot be the lattice, it cannot be the grain boundary. The reason is that the surface required less energy. So at the lower temperature itself, the surface can be activated and the diffusion kinetics can be enhanced. So these are the diffusion path. Later on, we talked about the misconception which was already always there, that the steady and the unsteady state. People say that the fixed first law is applicable only for the steady state and the fixed second law is applicable only for the unsteady state, and which is absolutely incorrect. Both the laws are applicable for both of them. Okay, so before I start, if you have any doubt, please feel free to put in the comment box. If not, let's move to the questions. The question number one. The question says that which of the following is an advantage of using low carbon steel for making gear? So see, we make the gears are like this. Uh, it has a lot of applications, but what we know that a gear will always be in the touch with the another part, and so the surface will always be under the action of the wear and tear. So what we know that the surface should be wear resistance. This should be a wear resistance. But you know the geometry, the way the shape of the gear is, it's a complicated shape. So for our material, should be in a way that it should be able to take this complicated shape. So what we mean by that, our material should have the good machinability. Good machinability, it means that the what we can say, we can refer to the low carbon steel. Low carbon steel have the good machinability, while the high carbon steel, if we see, if you go on the high carbon side, we get the good wear resistance. Okay, so what we need is surface should be having the high concentration of the carbon, and the bulk should be having the low concentration of the carbon, so that we will be able to machine them. So overall, what usually engineers do, they make the gear with the low concentration of the carbon, and then what they do, they put the entire gear in the chamber, which is having and in which the gas atmosphere will be of the carbon. So what will happen at the high temperature, the carbon from the atmosphere will diffuse to the surface, and it will take certain depth. So what we have achieved by that, we achieved that initially we, with the help of the low carbon, we got the good machinability, we were able to take the complicated steps. Now by the addition of this diffusion of the carbon from the atmosphere to the surface layer, we increase the wear resistance, we increase the hardness of the steel. Okay, so this is where the diffusion comes into play, and this is where the diffusion is very important. So the phenomenon of diffusion from the atmosphere to the inside is what it's important to us. Now the question says which of the following is an advantage of using low carbon steel for making clear? Okay, follow. Yeah, exactly. It's a better machinability, right? For the higher hardness, higher hardness, we need at the surface, and to achieve that, we do the process known as the carburization. With that, we have solved the question number one. If any doubt, let me know. If not, let's move to the next part, question number two. Fick's first law. Fick's first law of the diffusion states that the mass flux is proportional to the, which of the following will be the right answer? Yes, that's correct. The right answer is the concentration gradient. So the mass flux we are talking about J, which will be equal to the minus of d dc over dx. When we talk about the heat flux, let's say we are talking about the heat flux. In that, it is proportional to the temperature gradient. Now, when we are talking about the mass charge flux, for example, charge is moving in that way, it will be nothing but the gradient in the voltage, right? So here the conductivity will, okay, sorry, conductivity and the J. So the current density is proportional to the variation in the voltage. So all the flux are related with each other. Heat flux is the gradient in the temperature. The charge flux will be the gradient in the voltage, and here the mass flux is the concentration gradient. Where this concentration can be in terms of mole per meter cube, like mole per volume. One can also write it in the way that mass kg per volume. So whatever we use, we have to be consistent with that. Now one thing, the unit of the D is very important. In lot of the questions, once you visit the assignments question, you will find that the D has been asked multiple times. So what is the J? We know that J is nothing but here the mass flux, like the mass flowing per unit area per unit time. We are aware about this. Then we need to find the unit of the D multiplied by dc over dx. C we know is the, let's say we are using mass here, kg, so here also will be use the kg per meter cube. And here the distance unit is there, that is meter. So from here we can find the unit of the D, which is like this will be cancelled out, this will be cancelled, meter square will be there, so D will be meter square per second. Okay, so we can write like this. Okay, and this derivation we have studied in the class. So these are the list of the thing that we need to be keep in mind, that all the flux are related with each other, and the unit of the diffusivity is meter square per second. Good, let's move to the next part, question number 3. If there is any doubt, let me know. The question says, what does the Fick's second law describe? The relation between the flux and the concentration gradient, the relation between the rate of change of concentration and the spatial charge of flux, change of flux, the diffusion coefficient dependency on the temperature, the effect of the pressure on the diffusion. So which can be the right answer from all this? So we are talking about the Fick's second law. What we have just now studied is that the Fick's second law is the rate of change of the concentration with the time will be equal to the second order rate of change of concentration with respect with the space. Okay, yeah, that's good. The right answer is option B, and this is very important. Later on we see that when we solve that, we will get the C as a function of x and t, which can be given by A plus B times error function of negative of x over 2 root dt, where A and B are the constant. We don't have to be worried about that. Error function is just one of the function. For example, sine we have, sine theta. Sine is a function. Similarly, this is also a function. So if I know the particular time, if I know the at what depth, see, this is my surface. Just now we talk about the gear. Let's say this is a part of the gear. Above is the gaseous atmosphere. So the distance about at which we are talking about the concentration of a carbon, let's say, our concentration of the carbon is important. So the concentration of the carbon as a function of the space, as a function of the space mean as a function of the distance that is depth, and as a function of the time. This can be given as the by this x upon 2 root dt. One thing like, so this is something which we will remember, like the solution of this is given as this. Now in most of the questions things are little bit indirect, like you might be able to see a couple of questions in the assignment where they have used the word that the extent of the diffusion and or the concentration in the specimen remain constant overall in the case 1, in the case 2. For example, in one of the case, what one can do is they heated at the 500 degrees Celsius and heated at the 600 degrees Celsius, but they are varying the time and they told that the overall the concentration in the specimen is remain constant. So what does it mean? This part in the case of this 500 and in the case of 600, just by varying the time, it's constant. So our this part is constant, it means that they are already constant. So what is varying over here? This. So D is highly dependent upon the temperature. So at 500 and 600, this term x upon 2 is also constant, root dt will be equal to the x upon root dt at 600. And they will, since the temperature is different, and let's say they are talking about the same depth, the depth at which they are getting the same concentration. So what will vary is the time. So the questions will be asked in a way that you have to make sure that this will be remain constant. So what we will remember is that x upon root dt will be constant if the concentration profile is constant. Profile is constant or is same in given case A and B. So case A and case B can vary in variety of way, different way. One can also say that okay, the temperature was constant, but x and now they can play with the x and t. So what we have over here is a temperature which is governed by the diffusivity. What we have else is a space, that is a depth, and what we have is a time. So any one among them will be constant and two can vary. So we'll try to solve a couple of questions so that these things will be more clear. If any doubt in this, let me know. If not, let's move to the next question, question number 4. Now, this is a fundamental question. It's very basic. Like it comes from the derivation of the second law, Fick's second law. Fick's second law is derived using which fundamental principle? So we know that it has been derived, the derivation has been done from the conversion of mass, conservation of mass. Okay. So once we follow the derivation, we got to know that at particular profile it is making, we found that the amount of mass entering and the amount of mass leaving, and then from that whatever the amount of mass that was left over, that has been the one which is used to the change the concentration. But overall what we have concluded from all this entire the essence of the derivation is that the conservation of mass would be there. From this only this law has been derived. If any doubt, let me know. If not, let's go to the next question, question number 5. Question says, substitutional diffusion primarily occur through. So now we are talking about the substitution diffusion. Indirect interchange mechanism, vacancy mechanism, ring mechanism, diffusion through a grain boundary. Very good. Option B is the right answer over here. So we know that, let's say I have A atoms. And I'm heating it, temperature I'm increasing. So now what will happen? They will diffuse over here and it can diffuse over here also. What first one is saying, direct interchange mechanism, it is like this atom is going to this place and this atom is going to this place, which is very like energy required. The activation energy for this is very high. It's very high. There is also something ring mechanism. Instead of just two changing the place, the ring mechanism says that they will form the ring and they will change their place. But this is also very unlikely to happen. So because the energy is very high. So this both the mechanism has been eliminated, and the vacancy mechanism for the substitutional diffusion is the one which is dominated. Diffusion through the grain boundary, it's a grain boundary diffusion mechanism, it's not the substitutional diffusion. So we can say, yeah, it's a grain boundary. Any doubt in this? Let me know. If not, let's move to the next part, question number 6. In the substitutional diffusion, the presence of that is essential for the atomic moment. Very easy. Just now we have discussed. It's option B. Yeah. So the vacancy is required for to do this. Now let's go to the next question if there is no doubt. Question number 7. Now this type of questions, like once we visit the assignment of this particular week, we'll see there is a lot of numericals. Okay, I think I found around 4 to 5 numericals. So I make sure that my this particular dot solving sessions, I should try to cover the as number of numerical as possible from my side. Let's go to the question number 7. Find the diffusivity, that is D, of a material with a D naught is given to us, D naught is given, and the activation energy Q, that is Q is equals to the 50 kilojoule per mole at 100 degrees Celsius. The temperature is given. We have to find D at this particular temperature of 100 degrees Celsius. D naught is given to us. We know the expression how D change. D is equal to the D naught exponential minus of Q divided by R times T. We have all the values available to us. Let's try to substitute them. D will be equal to the D naught. D naught is also given meter square per second, right? And which is the required. So we don't have to change anything in this particular unit. So we'll write 5 multiplied by 10 to the power of minus 3 exponential minus of Q. Q is given to us in 50 kilojoule per mole. Okay. But you can see the unit of the R and T. The unit of R is joule per mole, right? Joule per Kelvin per mole. So what I will do, I will try to I will convert this kilojoule to the joule itself, multiplied by 10 to the power of 3. Okay. I multiplied by 8.314 into T. T will be 100 degrees Celsius, so we'll take in the Kelvin. It will be 373 Kelvin. Now once we solve, we'll easily get the answer. Let's try to do this. Multiplied by 10 to the power of 3, 8.314 multiplied by 373. So we can get the answer is D is given to us 4.97 into 10 to the power of minus of 10. Yeah, that's right. The option C is the right answer over here. 4.97 to 10 power minus 10. It was very easy questions. If we want to find the D, so now we can find D at any particular temperature, any temperature that is required. As long as we know the activation energy, as long as we know that D naught, we can find the diffusivity at any particular temperature. Okay, any doubt in this? Let me know. If not, let's move to the next part, question number 8. This is something that we have discussed at the initial section of our dot solving session. One of the major factors that makes substitutional diffusion slower than the interstitial diffusion is what? Why substitutional diffusion is slower than interstitial diffusion? The reason is very clear. In interstitial diffusion, we only need the, what we have to do is the activation energy is only for the migration. While for the substitutional diffusion, along with the migration, we also need the extra energy for the formation of the vacancies. You will see that the diffusions are, in the case of the substitution, when we go to the very high temperature, our equilibrium concentration of the vacancy also increase, and that's why the substitute this also increase, the diffusivity is also increasing. So now here, what it is? It's the enthalpy of formation of the vacancy. Okay, so the option A is the right answer over here. Any doubt in this? Let me know. If not, let's move to the next part, question number 9. It's very easy. We have already discussed this part. Again, we'll have a quick look on this. Choose the correct order of the activation energy of the diffusion. So what we have is a lattice diffusion. We have grain boundary and we have surface. These three we have to arrange in an order. Yeah, very good. That's the right answer is option A. The activation energy for the grain boundary is the highest. Then lattice diffusion will be the highest, and then grain boundary, and then the surface. Okay, so it's very easy to move along the surface. Then it's the grain boundary, and then it's the lattice. Very good. Let's move to the next part, question number 10. Now this question. At 100 degrees Celsius, at 1000 degrees Celsius, what is the time required to carbonize the steel with an initial composition of this to the composition of this at a depth of this? Okay, a carbonizing atmosphere provides a constant surface concentration of this. The diffusivity of C, the diffusivity of carbon in the gamma is given to us. D naught and Q is also given to us. The error function is given to us. What we have to find? We have to find the time. Time required. All we have to find here is the time required for the carbonizing a steel. This is our question. And this we can find. Let's formulate our approach to do this. We know concentration at any particular location minus initial concentration divided by concentration of the surface minus initial concentration. Okay, it will be given to us that the error function of minus of x upon 2 root dt. Okay, so here we have Cx, C naught we need, concentration at the surface, concentration at the again initial concentration. The x is given to us, that is we need at 0.2 millimeter. So x is given. X is saying it's a 0.2 millimeter. What we need to find? We need to find the time required. That is T is the unknown. What about the Cx? The concentration at the depth of 0.2 is required to be the composition of this. Okay. We need to make it 1.11. What is the initial concentration? Initial concentration is always is given to us 0.29. Okay. A carbonic atmosphere provide a constant surface concentration. So surface concentration is always constant. So Cs is given to us, that is 2. we know this C naught, Cs we know, Cx we know. So left hand side we already know all the factors we know. Now on here we need to find the time. We know x, so d is also required, right? And d is given by the d equal to d naught exponential of minus of q over rt. Now what is the temp? See, d naught is given to us and q is given to us. Okay, and the temperature is also given. So the T is given, that is we are doing at the 1000 degrees Celsius. Activation energy is given, that is 150 kilojoule per mole. And D naught is also given, that is 7 multiplied by 10 to the power of minus 5 meter square per second. Right. So with all these known factors, we can find D, and then we just have to solve this error function. So this is our approach. Now let's try to do it. Okay. First aim will be to find the D. D is equals to the D naught, that is 7 into 10 to the power of minus of 5 exponential of minus of Q, that is 150. Again, it's a kilojoule is given. So what I will do, I will convert to the joule divided by R, that is the value of R should be given and the unit should also be there. If not, we'll take the 8.14 joule per mole Kelvin multiplied by the temperature. We will always prefer the Kelvin. Okay, so what we'll do, 1273 Kelvin. Now can we quickly find the value of D from this? Let's try to do this. So we got the value of D. Okay, I think my values are differing from the yours values. What I'll do, okay, the value of R 8.314 will take. So it will come 4.89 into 10 power minus 11. That's right. 8.314. So the value of D will be 4.89 897 into 10 to the power of minus of 11. So we found the value of D. Unit we will write, that is meter square per second. Now let's try to find this value, Cx minus C naught divided by Cs minus C naught. Cx is given to us 1.11 minus C naught is 0.29 divided by the surface concentration is always 2 minus C naught, that is 0.29. It will be equal to the error function of minus of x. X is 0.2 mm, right? So what we'll do is we'll convert this into the meter, 10 to the power of minus of 3 divided by 2 root over D. D we just found 4.897 multiplied by 10 to the power of minus 11 and multiplied by the time which is required. Now let's try to find this. It is equals to the 0.4795 error function of something. So now let's see what is this error function the value is. Okay, so this is Z, and error function of Z is 0.4795, that is what we have got. 47, so somewhere we are very close here. So what we'll do is the value of Z, see the error function of Z, let's say this is my Z, and the value of Z we have, error function of Z we have got this. So the value of Z should be 0.45. So this value will be nothing but it will be equal to the 0.45. So for that only, for this type of questions only, we give the error function table. You will also find in the assignment similar question, and you will find that the table will be given to you. Now we have to solve this. Let's write the equation that we have to solve. That is 0.45 will be equal to the, it's very easy, 0.2 multiplied by 10 to the power of minus of 3 divided by, just a minute guys, 2 root over, okay, x will, since it's negative, so we'll make it a positive, and 2 root over 4.897 into 10 to the power of minus of 11 multiplied by t. Now from here we just have to find the t. It's very easy. What we'll do is we'll just rearrange the term. T will be equal to the 0.2 into 10 to the power of minus of 3. The whole square I'll do on all the sides, on both the sides, divided by 4 multiplied by 4.897 into 10 to the power of minus of 11 multiplied by 0.45 square. So let's quickly do this. Nine into 10 power minus 4. Okay, that will be the right answer maybe. Let's just clarify. The time is given to us 9 into 10 to the power of minus 4. Okay, just let's have a look. So what we'll do is 0.2 multiplied by 10 to the power of minus 3 divided by 4 multiplied by 4.897 multiplied by 10 to the power of minus 11 multiplied by 0.45 square. Okay, so what I have got over here is the time required is 1008 seconds, which is like a reasonable amount. Like, and now if we convert it to this particular time to let's say hour, how much we'll need is around 0.28 hour. Okay, 9 into 10 power minus 4. Please revisit your calculation, because see, the factor of 10 to the power minus of 11 is here, and that can change the entire thing. Okay, if this part has been not included, then it will be incorrect. So at this particular temperature, if you want to achieve the concentration of 1.11, starting from 0.29 at the depth of this in the austenite, then you will need to heat it in the atmosphere, where the carbon percentage is 2%, the atmosphere carbon percent is 2%, and the time for the amount of time that you have to heat, you have to put it in this particular atmosphere is 0.28 hour, that is 108 seconds. Okay, so this is the entire the procedure that we have followed. The question is little lengthy, I agree with that, but it's easy also. Our entire theme is based upon this. We need to carefully find that what is given to us, what is like at particular depth, what is the concentration, what is the initial concentration, what is the concentration at the surface, and then we need to find the depth was already given to us. I found that I need this d also. So d we need to be found by d naught exponential minus q upon rt. All the values were given to us, q, t, and d naught. Okay, if any doubt, let me know in this question number 10. If not, we'll move to the next part, question number 11. I have 4 more questions left. Okay, seems like there is no doubt. Great. Let's move to the next part, question number 11. The question says, if the activation energy for diffusion is this, activation energy is given to us 70 kilojoule per mole. At what temperature will the depth of diffusion be 10 times that at the 25 degrees Celsius for the same diffusion time? Okay. So, see, in this type of questions, what we got, that they are not discussing about the concentrations. So the equation which we wrote, the left side is already, it's not been discussed. It's mean that it's a constant. Since this is a constant, it means that this is a constant in both the cases. It means that x upon 2 root dt is a constant. So in the both the cases, x upon root dt is constant. In the case 1 where the temperature was this and the sorry where the temperature is T, and in the second case where the temperature is 25 degrees Celsius. Now let's try to find this. Okay, one thing, for the same diffusion time, now you can relate that same diffusion time, it means that the T is also constant. So what we got, if we move, since this is a constant, let's move to the other side. So x upon root d is the constant now, k dash. What we have to do, we have to equate both the things. X divided by root d will be equal, at that particular temperature T should be equal to the x upon root d at a particular temperature 25 degrees Celsius. Now what we have to find is d. What we have to find is t. T is the question mark. One thing is given between the relation between the x. The relation is given as if the activation energy is at what temperature the depth of diffusion be 10 times, okay, 10 times of which the one which was at the 25 degrees Celsius. Okay, so this will be, so the depth at particular temperature T is 10 times the depth at the temperature of 25 degrees Celsius. So we can substitute over here, and what we'll get is the here. Let me take the new page. It's little bit getting hopscotch. We wrote x upon root of d at the temperature of T. It is equal to the x upon root of t at the temperature of 25 degrees Celsius. So we can just write in this way also, and x at 25 degrees Celsius divided by root of d at 25 degrees Celsius. Easy. What we knew is that the relation was given in the question that it is equal to 10 times x at 25 degrees Celsius. Let me substitute this over here. What I will get at this place, I will substitute this 10 times x of 25 divided by root of d at particular temperature T is equals to the x of 25 degrees Celsius divided by root of d at the temperature of 25. So this and this got cancelled. Now it's very easy. Root of d at the temperature T and root of d at the temperature of 25 multiplied by 10. Okay, so now we can square them. 100 times d of 25, it will be d of t. We know the relation. D is equals to the d naught exponential minus q upon r t. Let's substitute them. 100 times d naught exponential minus of q divided by r. T is nothing but 25. 273 plus 25, it will be the 298. And it will be equal to the d naught times exponential minus of q divided by r. The temperature is unknown. Now this, let's quickly have a look on this. I will not completely solve. It's just a numerical right now. D naught is cancelled. The value of Q, the value of Q is given to us. Activation energy was given that 70 kilojoule per mole. 70 kilojoule per mole, which we can obviously convert to the joule per mole multiplied by the 100. So the question is, the answer is 5. Here the answer is given to us. Okay. See, obviously, a 5 cannot be the answer. The reason is that the temperature, if the diffusion is higher, we know that at this particular temperature the diffusion is higher. It means that the temperature should be higher than this. It will always be more than 25 degrees Celsius. Okay. So we have to solve this, and what we will get is the value of R is also we know. The Q is also we know. Seems like you are facing problem in the solution. Let me complete it then. So the 100 times exponential of minus of Q divided by R 298, it will be equal to the exponential of minus of R divided by T times of R. Let's shift the exponential term on the one side. 100 will be equal to the exponential minus of Q upon RT minus Q upon 298. Okay, we can take ln on both sides. Log of 10 will be equal to the minus, also I will shift this side, Q upon RT minus Q upon 298 times of. Let's substitute the value of all of them. Okay, now what I have to find is the value of T. I will try to do one thing. I will isolate this particular T and will move everything on the other side. Let me move this over here also. Q upon 298 R minus of ln 100 will be equal to the Q upon R times T. T will be equal to the Q divided by R times Q upon 298 R minus of ln 100. Now this is the equation which we have to solve. Let's write it down. The value of Q I will substitute in the terms of the 70,000 joule per mole. R you have already told me 8.314. Let's substitute the value. I think my calculator is visible. That is Q 70,000 divided by R is 0.314, right? I have to multiply them with this entire term, that is Q, which is again 70,000 divided by 298 multiplied by R 8.314 and minus of, everything is right, yeah, minus of ln 100. Okay, so what we have got, the value of temperature, the temperature is 356.03 Kelvin. In the question we see all the units are in the degree Celsius. Let's quickly subtract them. 273. What we got the answer to be, the temperature is 83 degrees Celsius. Okay, so the right answer is option C. If any doubt in this, please let me know. If not, we'll move to the next part, question number 11. Okay, seems like there is no doubt. Let's move to the next part, question number 11. Great. Sorry, question number 12. The pro-eutectoid phase form, that's the eutectoid temperature in dash. Okay. The pro-eutectoid phase form above, below, or at eutectoid temperature. What is the meaning of pro-eutectoid? Pro-eutectoid means pro is something like that has been happened before itself, right? So now let's see here. Okay, eutectoid. What is the eutectoid reaction? We know that eutectoid is a reaction where a solid, let's say gamma, is converting to the ferrite and cementite. This is a reaction which is happening at this particular point. The gamma is converting to the ferrite and cementite. Now let's say I'm starting with this composition, or I'm starting with this composition. What is going to happen? Initially, this is alpha and this is alpha and this is gamma. Here the mixture of alpha and gamma will be there. Eutectic reaction will happen only at this particular point, right? So starting with this particular composition, we are keep lowering the temperature, What is going to happen? Eventually this alpha, the gamma composition will reach here and the reaction will happen. So whatever before this particular temperature, the reaction has happened, that is nothing but a pro-eutectoid. That is will happen before, that is at the higher temperature, that is above, right? Now whether it's a hypo, that is less than 0.8%, or whether it's a hyper, in both the cases this is going to happen. The pro-eutectoid alpha will form above this eutectoid temperature, that is I think 725 degrees Celsius. Yeah. And it happened in both the cases, hypo and the hyper-eutectoid state. So the option C here will be the right answer. If any doubt in this, let me know. Great. Since there is no doubt, we can move to the next part, question number 30. This is the similar type of questions. What we'll try to do, we'll formulate the idea how we are going to solve this. The diffusion coefficient of copper in aluminium at this and this are given to us. Okay. Determine the approximate time at 500 that will produce the same diffusion result at 10-hour heat treatment at 600. Now, important, see, few points be very hidden in the question, which we have to find. Produce the same result, diffusion result. It means that the concentration part has already been constant. So what is the variable? X upon root dt. Okay. Now, they are not even discussing about the depth, and the depth is also constant at that particular thing. So the X is also constant. So what is the varying? D into T is the constant. D into T is the constant in both the cases. So D into T in the case of that would be the same result at, let's say, 600 degrees Celsius. It should be equal to the D into T, which is the result which is produced at the 500 degrees Celsius. Right. Diffusion coefficient is given to us, that is D is given to us. Okay. So now let's try to formulate. We just have to put the values over here. The diffusion coefficient is at 500 is given to us, that 500 and 600. 500 is 4.8 into 10 to the power of minus of 40. Unit we can see here also, 5.3 into 10 power minus of 30. Okay. Determine the approximate time at 500 degrees Celsius. This is unknown. That produces the same result for heat treatment at the 10 hour. Now, very simple. See, the temperature is low. Here the temperature is high. At high temperature, the time required is the 10 hour. Low temperature, time required to produce the same result, it will, by intuition we can say that it will be higher, Okay, it will be higher than the 10 hour. The time required will be higher than the 10 hour. Can someone quickly answer this? What is the time required over here? All the values we have with us. So what we have to find is t here. T is given by 5.3 into 10 to the power of minus of 13 multiplied by the 10 hour divided by 4.8 into 10 to the power of minus of 40. Okay. What we can do is we can cut them and we can add extra 0 over here. 5.3 multiplied by 100 divided by 4.8. So we can see how much time is required. Time required is 110 hours, approximately 110 hours. Here 10 hours was required as 600. Here we can see how much 110 hours is required when we are treating at the 500. So this is how the beauty of the diffusion is. If you increase the temperature further to 700, the time required instead of 10 it can brought to the 1 or even less than that. That can depend upon the calculation. Okay. So with that we have completed this question number 13. Let's go to the last question of this particular session. It's very easy. All of us can answer this. We have to match the lattice diffusion with the activation energy, surface diffusion, grain boundary diffusion, dislocation diffusion. Okay. 1, 2, 3, 4. So first one, lattice diffusion is going to match with the option A, highest activation energy. That's right. The second, surface diffusion. Surface diffusion will be the lowest activation energy. Option B. Grain boundary, it will be somewhere in between the lattice and the surface. So they are following like this, the same row itself. The dislocation diffusion is the one where the defect assisted diffusion occur. Okay. We also call the dislocation diffusion as a pipe diffusion. Where a dislocation is acting like a pipe, along which an atom or a vacancy can migrate, like from whichever angle you want to see, whether you see from the perspective of the atom or whether you see from the perspective of the vacancy. Both are indirectly same itself. So these are the list of the questions that I wish to cover, and my intention was to make sure that you are easily you are able to solve the questions of the assignments. Okay, so please let me know if you face any difficulty in this particular today's discussion. Then we can again repeat couple of things, and if you are facing any difficulty in the last for example last week questions or any assignment question, that also we can discuss. We have got one question. Let's have a look. So can you explain eutectic, hypo-eutectoid and the hyper? Very good. Yeah. Fine. So here, let us make a phase diagram of the iron carbon itself, and we are only focusing on the eutectoid reaction. So this is my gamma iron, and this composition we know that this is 0.8. Okay, what is a eutectoid reaction? Eutectoid reaction in the iron right now, if you are talking about the iron carbon diagram, the gamma, the austenite will convert to the ferrite and cementite. This is a reaction. Okay, so here is alpha, here is alpha plus gamma, here is a gamma plus Fe3C, and here we are forming the alpha plus Fe3C. Now when we are talking about the eutectoid steel, it means that we are talking of this particular composition 0.8. Eutectoid steel mean that the carbon concentration is carbon percentage is 0.88%. Okay, it will have a microstructure. It will look something like this. Why I'm drawing the line? It's like the middle portion we can call it Fe3C, and this portion we can call it the alpha ferrite. So it's a laminar structure of ferrite and the cementite. Now for the hypo, hypoeutectoid steel. Hypoeutectoid steel we call when the concentration we are talking is less than the 0.8. So the carbon percentage will be less than the 0.8. Okay. Now the last part, hypereutectoid, is the one where the carbon percent is more than the 0.8. Okay. So for example, if we are dealing with something like this. So now let's see the how the microstructure is being evolved over here. If we talk about this particular point, in the case of hypoeutectoid right now, sorry, in the case of eutectoid still we are talking about, what we are getting? We are getting the microstructure entirely consisting of the gamma alpha ferrite at this particular temperature. Now over here, what we can see, so what is happening over here is that entire thing is converting to the microstructure which look like this, where the mixture of the ferrite and the cementite will be there, and it is like a micro constituent, which we also call this mixture, we call as the perlite, which is a micro constituent made up of the ferrite and cementite. Now we discuss about the eutectoid steel. Now what about the microstructure, how it will evolve in the case of hypoeutectoid? Let's talk, we are currently in the temperature where only the gamma phase will be there. So the microstructure still will look like this. All the places gamma will be there. Now let's talk about this particular point. We have not crossed the eutectoid temperature yet. 723 we not crossed it. So the reaction has not been done. So what is the microstructure at this particular point? What we'll do is the gamma was there. Let's draw the gamma. Everywhere gamma is there. It is austenite is there. Now at the green boundary, the alpha will also start to form. So this is alpha. Okay. Now when we came down, now let's say now we are talking about this particular how the microstructure of this will look like. See, we remember here that a couple of the ferrite also form. How the microstructure will look like now. Initially formed ferrite will be there. Okay, this is ferrite. Now in the remaining where austenite was there, now there will be the micro constituent. Okay, here the micro constituent will be there. So this micro constituent will again be made up of this ferrite and cementite, Fe3C and Fe. It is alpha ferrite. So now in this microstructure we can see that we have the alpha ferrite in two different structure in two different way. One which is coming the pro-eutectoid, like the question which we discussed, the pro-eutectoid ferrite. So there what we can see is that alpha ferrite we have which is already formed. How this will be dispersed like this. While in the case of once the reaction has been completed, one more ferrite will be there when it will have a lamellar structure with the cementite. This is what happened in the case of hypereutectoid. Now let's talk about the last part, that is a hypereutectoid. Here the structure will remain as it is initially. Now here, instead of forming the ferrite, what will form at the grain boundary is the cementite. Okay, so in this structure the cementite will be there, and along with the cementite, proeutectoid cementite, once we come down to this particular temperature, this type of structure will form. Okay, so this is how the hyper and eutectoid will be there. Okay, so these are the key difference between these three different type of steel, and the major part we have to remember is that hypo will be less than 0.8, hyper will be more than 0.8, and the eutectoid steel will be the 0.8 weight% of the carbon. Let me know if it is clear. Great. Any other doubt, guys? Please let me know. If not, then we can wind up today's session, and we can meet in the next week, week 9. Before I complete, I would like to again ask you that if you have any doubt regarding the assignment itself, if you are not facing any doubt right now, and you are facing like, okay, while solving the assignment, you are getting some doubt and you want to clarify, please put it on the Q&A forum. Okay. Okay. So with that, we can wind up today's class.